Hey everybody, it's me, Steve. It's about 22:30 on February 3rd, 2017. Temperature's about 17 degrees Fahrenheit out. It's cold. Anyways, I'm heading back from a birthday party. Happy birthday, Lori. And I'm still not feeling very well. This head cold, it just won't go away. But anyway, so if I cough or something, I apologize in advance. But today I want to talk about faults. So what's a fault? Talking about faults, I'm talking about geologic faults here. I'm not talking about somebody who screwed up. But a fault is just a planar surface, relatively planar surface, where measurable movement has occurred. You know, like two rocks, bodies are up against each other, one slips, slides. Okay, it's that surface, that plane. That's the fault. Of course, they're not always straight. Usually when we measure them in the field, that little part is straight. But what exactly is meant by measurable movement? Well, measurable movement depends on your scale. Some people deal with microfaults, and there can be less than a centimeter of displacement. But usually as field geologists, basically our reference point is any fault that's mappable at the scale we're using, usually at a 1 to 24,000 scale. So for a fault to be mapped at like that, depending on the geology and how other things are, basically it would be the movement on the size of a person or larger. Generally it's hundreds of feet. Like I said, it depends on what you're mapping and how the related beds are deformed and whatnot. But rocks in general will behave like fluids over time. What that means is they want to bend. Like they want to bend. You get things like anticlines, synclines, things like that. But that's called ductile deformation. But sometimes they break. That'd be your plane. That's brittle deformation. That's when you get a fault. There's many different types of faults. You have normal faults where one drops down. That's caused by extension. You have reverse faults, like one drops up against another. That's compression. And reverse faults that are low angle, something like that happens. That's a thrust fault. Just call it that. You can also get faults like if you're looking down. My hands are the surface. This isn't a cross section. They move this way or that way. That's strike slip. Now, usually faults are a combination of these. But when people hear the word fault, they usually think of active faults like San Andreas and Madrid. And there's a lot of active faults, and basically any places where the continents are splitting apart or pushing together and one's subducting. Not a continent, but there's more plates subducting. You have active faults. But Earth, the crust of the Earth, is one big, huge, random jigsaw puzzle where the movements didn't care about what piece went where. They just moved it until the continents just moved until things fit together. And faults are actually very, very common. 99.9% of them, I would say, aren't active. As a matter of fact, there's a 80-mile long fault in northern Illinois in the bedrock. It runs from Will County west-northwest to Ogle County. It's not active. And just to the west of that one, they don't connect, but they're close. They have to come within 10 miles. Begins another one called the Plum River, which extends from Ogle County west 120 miles into Iowa. These are common. And that's just on, the stable part of the Midwest where most of the bedrock is relatively flat. When you go back in time even further, you tend to get more faults. Because older, like Precambrian rocks, Archean rocks, have been highly deformed and highly faulted, but they're just not active. And they're common. I've done mapping in the Upper Peninsula in Ontario where I've drawn fault lines under people's houses. Are they at risk? No. I mean, that fault moved 3 billion years ago. It's not going anywhere now. You still need, in order to keep a fault active, you need active stresses, either compression or extension. Once that goes from the area, the fault just dies. And faults can sometimes heal, if you will. I mean, they're still displaced, but you can get minerals in there or compression enough to where it's hardens and becomes like a suture. But like I said before, rocks, they like to deform. You can think of it, a lot of people, this confuses a lot of people. They're like, well, how can something as solid as a rock bend? Well, it's most people think of, without getting into elasticity and all that, the physics of it. Basically, you take a solid and move it slowly over time, especially something like a rock unit that's buried or whatever. It behaves more like a fluid. So you can think of silly putty. Silly putty is like a perfect example of this. Okay, silly putty. You pull it slowly, and it bends, it deforms. Okay, you pull it quickly, and it breaks, it snaps. Sorry, I'm holding the camera right now as I get off on this ramp here. And that's kind of how the rocks behave. And also, rocks will want to tend to bend more if they're deeply buried. They're under heat and pressure because they're warmer. They're more likely to bend than they are to break. So rocks can behave like fluids over time. Like I said, sometimes they're brittle and they break and they form faults. And faults are very interesting because they kind of tell you what the continents were up to during that time. If you can lock down the age of a fault, you can find out a lot about the tectonics of that area, even if it was 2.5-3 billion years ago. And there are some faults that we're just not exactly sure what's going on. We call those crap. It's eluding me right now. I just had it in my head. But anyways, I got it. Okay. If faults that are over dozens or hundreds of miles that have healed really well, like said, healed, filled with whatever, we call those, I just lost it again. Wow, I must be tired and sick. We call those, crap. I can't believe I forgot this. I had it and I lost it. Wow. Not sutures. That's not the correct word. I don't know. I'll try to think of it here in a second. But anyway, these long faults over hundreds of miles, they kind of like merge in, like you get one rock type next to another, and they'll just kind of, I wouldn't say merge into another rock type, but there's a gradation between rock types, but there's definitely been large-scale movement. It's just not obvious. Shear zones. It's a shear zone. That's what it is. There's a lot of these in like the Upper Peninsula, in the Precambrian rocks and stuff like that. We're not exactly sure why that happens. It's kind of a special case fault, and likely what has happened is, obviously you had a mountain building event. You may have had a situation where two continents collided, and when continents collide, they don't like to subduct, so you'll get like these, it'll move in weird things because continents don't want to subduct back into the mantle. Usually when two plates collide, say one's a continent, one's an ocean, the ocean's always going to go under. Okay, that's why we don't have ocean crusts older than, I want to say, late Triassic or early Jurassic. Yet we have rocks at the surface that are, over 4 billion years old. So, but when two continents collide, one doesn't want to go under, and that's kind of happening with the Himalayas right now. You might get a partial slip, but eventually that's going to stop. Okay, and that's probably what produces these shear zones. You get grinding, one wants to go under, doesn't want to do it, so they start moving laterally or whatever. But I just wanted you to know that that faults are very common, and that they are just about everywhere. Active ones are the only ones you have to worry about. But that's my rant for today, and I hope you learned something.